In 1913, a roulette wheel at the Monte Carlo Casino landed on black 26 times in a row, and it cost gamblers millions of francs before the streak even ended. Here's why that happened. Everyone at that table believed probability owes you something. Flip heads 5 times, and red suddenly feels due. Miss 10 free throws, and the 11th feels destined to go in. Wait long enough at a bus stop after 3 late buses, and the next one feels guaranteed to show up early to apologize. That's the picture almost everyone carries in their head. Probability as a fair referee, quietly balancing the scoreboard so things even out on your timeline. Probability isn't balancing anything. Each spin of that wheel has zero memory of the spin before it. The odds of landing on black 26 times straight were about 1 in 66.6 million, genuinely rare. But once it happened, the wheel forgot instantly. Betting red on spin 27 was still a 50-50 coin flip, not a correction owed to anyone. The gamblers weren't unlucky. They were reading a memory into a machine that has never once kept score. It's called the Monte Carlo Fallacy now, which is a fittingly polite name for, the wheel does not care about your feelings. So why does the math seem to promise a correction if it never delivers one? Because there is a real law hiding underneath the wrong instinct, and it's just aimed at a completely different scale than your brain is using. Jacob Bernoulli worked it out in 1713, in a book his nephew published after Bernoulli's death, calling it the law of large numbers. Flip a coin 10 times and you might land on 8 heads, no correction in sight. Flip it 10 million times and you land almost exactly on 50-50. The law is real, and it's not a small exaggeration to say how different the scale is. Bernoulli's proof only kicks in somewhere around thousands or millions of repeats, not the 10 or 20 attempts your gut treats as enough data to expect a correction. You're not wrong that things even out eventually. You're just applying eventually to a timeline about 6 orders of magnitude too short. That mix-up isn't just a casino problem. It's a wiring problem. Psychologists Amos Tversky and Daniel Kahneman named it in 1971, belief in the law of small numbers. They found that even mathematically trained researchers assumed a tiny handful of results should already look like the long-run average. The deeper mechanism behind it is something Tversky and Kahneman later called the representativeness heuristic, the brain's habit of judging how likely something is by how closely it resembles a familiar pattern, rather than by actually counting how much evidence is in front of it. Here's the part that actually explains the failure. Our brains are built to spot patterns fast, using as little data as possible, because that's what kept us alive around unpredictable predators and unpredictable weather. That same shortcut is completely useless at a card table, where 10 hands tell you nothing, but it fires anyway, confident as ever. That shortcut even fooled science for 30 years. In 1985, Thomas Gilovich, Robert Vallone, and Tversky went looking for the hot hand in basketball, the belief that a player who just made 3 shots is more likely to make the 4th. They checked real Philadelphia 76ers shooting logs, then ran a controlled experiment with Cornell's own team. Both times, hot streaks looked statistically identical to random noise. Case closed, the hot hand was declared a myth, another story fans tell themselves about coincidence. Except in 2015, economists Joshua Miller and Adam Sangiorgio found a quiet flaw in the original math, a bias that makes it artificially hard to detect a hot hand inside any short sequence, even a genuinely hot one. Once they fixed it, a small real hot hand effect appeared, which means the researchers studying everyone else's bad instincts about probability had a bad instinct about probability too. Nobody, including the people whose entire job is catching this exact mistake, gets to feel superior about it. Francis Galton ran into the same illusion in 1886, first on sweet pea seeds, then on human height. Unusually tall parents tended to have shorter children, unusually short parents had taller ones. Not because nature was correcting anything, but because extreme results are partly chance, and chance doesn't repeat itself just because it happened once. He called it regression toward the mean. A rookie's incredible debut season, a stock's wild quarter, a sudden slump the year after, none of it is a correction. It's just chance letting go of an extreme result it was only ever loosely holding on to. This isn't only a casino or a sports bar argument, it shapes decisions that actually matter. In 2016, economists Daniel Chen, Tobias Moskowitz, and Kelly Shue studied asylum judges, loan officers, and baseball umpires, 3 groups trained specifically to be objective. All 3 still showed the Monte Carlo fallacy in their real rulings. An umpire who's called several balls in a row starts calling the next close pitch a strike more often. A judge who's approved several asylum cases in a row gets noticeably stricter on the next file. This is the part worth sitting with. These aren't careless people. They're some of the most trained, most scrutinized decision makers there are, and the bias still got through. Because it isn't a knowledge gap you can study your way out of. It's a wiring default, and expertise doesn't switch it off. It just makes the mistake look more official when it happens. Businesses have noticed this bug in your brain, and some of them are built to profit from it. Powerball odds sit around 1 in 292 million, yet people still avoid unlucky numbers or hand-picked birthdays, as if the machine drawing balls has opinions about which ones it's touching. Modern casinos post digital scoreboards above roulette tables showing the last 20 results, not to help you, but because a visible color streak reliably makes players bet harder against it. Even Wall Street runs on this. A 1997 study by economist Mark Carhart found that hot mutual funds mostly failed to repeat their hot streak the following year, yet investors kept pouring money into last year's winners anyway, chasing a heat that statistically wasn't there. So here's what actually changes. Probability was never describing you in the first place. It describes millions of instances you will personally never live through. You only ever get one draw, one game, one ruling that matters to you, and the math was built for the aggregate, not the single moment you're standing in. That gap, between a formula meant for a million trials and a life that only gets one, is exactly where the word luck lives. Probability is the average viewed from far enough back that it blurs into a smooth curve. Luck is what that same curve looks like zoomed in on your one point on it, close enough that the smoothness disappears, and all you can see is your own results staring back at you. Luck isn't the opposite of probability. It's the name we give probability once we're standing inside one single result, instead of watching the long average roll in from a safe distance. Monte Carlo didn't lose because the wheel felt guilty about spin 26. It lost because a room full of grown adults trusted a memory that spin 27 never agreed to keep, and if you've ever felt a streak was due to break, you've trusted that exact same imaginary memory. If this is the kind of quietly broken logic you like having explained, stick around. This channel finds a new one of these every week.